So circuit means closed path where a current can flow. Network means there can be a current flow or there cannot be a current flow. So in this particular figure, you can see that A, B, F, E, A. It is a loop. All the loops are circuits. So this is a loop. When you start from here and if you are moving towards this, you can see that it will again come to the path A, and here current can flow because the complete path is closed. So you can also call it as a loop. Okay, so here that is one thing. So that is called as a loop where current can flow. That is can also called as a circuit. Okay, so if you see BEDCB, so in this path here between C and D there is no connection. So since there is no connection here, current cannot flow. So you can call this as a network. Okay, so it can be either open or closed, and this ABFEA. So ABEFA. So this is a only closed, and this can be either network or circuit. Okay, so let us proceed. So other than this, these are there are certain circuit elements. So interconnection of electrical elements is called as electrical circuit. In circuit analysis, which you are going to read in your principles of electrical engineering and measurement, what we are basically going to do is we are going to find current and we are going to find voltage, or based on current and voltage we are going to find some other thing. Okay, so that's what we are going to do. So that we call it as a circuit analysis. Okay, this circuit is mainly comprised of two things. One is active element and another one is passive element. You can consider active element as an element which can supply energy for certain period of time. Okay, similarly passive element is an element which can only absorb energy, or it can supply how much amount of energy it is absorbing, it is going to supply. Okay, for example, active element you can consider battery is an active element. Battery is an active element. It can supply power till how much it is charged. Okay, so this battery is basically called as a voltage source that we will see later on. This will be generally called as voltage source. Okay, the passive element generally we say it as say resistor, inductor and capacitor as passive element. Okay, this inductor and capacitor, as you know very well that this inductor and capacitor can also discharge, right? But how much it can discharge is how much it is charged, till that only it can discharge. Okay, so this resistor, inductor and capacitor, those things are called as passive element, and active element is an element which can able to supply energy, and you can also say that it can able to supply power. Okay, so here you have mentioned operation amplifier. Actually operational amplifier, this is also called as an active element. The reason is as of now you don't you will not understand that. As of now you do not know maybe what is operational amplifier also. So operational amplifier is also called as active element. Okay, and passive element, the net power will not be greater than zero. Okay, the net power will be less than zero, means it always consumes power. This is going to supply power for certain period of time. Okay, so that is the basic difference. Other than that, this active elements are broadly classified into two types. One is voltage source and the second one is current source. Okay, so these sources are again classified into independent source and dependent source. Okay, so if you have independent and dependent, these are the main classification for the active elements. You can also consider, or you can consider that this active elements comprised of voltage source and current source. This voltage source again it can be independent voltage source and it can be dependent voltage source. Similarly, the current source you can consider dependent current source and independent current source. Okay, what is that we will see later on. So in general, For independent current source, we will be representing like this. You can see that this is a voltage source. Independent voltage source will be represented as circle. Within that, we will be having plus and minus symbol or polarity, you can call. This is a battery symbol. This battery can also be called as independent voltage source. Okay, in general, these sources, okay, including this, the current source can be represented as like this. How I have represented is a circle is there, then within that an arrow mark is represented. This represents the independent current source. Okay, similarly, the voltage source, you put a circle, then within that you mention plus and minus. Then similarly for battery, you mention a bigger dash and a smaller dash, so you mention like this. So these are called as independent source. Okay, then this independent source will be further classified, that we will see. In general, whatever do we study, we are always discuss about ideal independent sources. Okay, there are two kind of things again in the independent source. One is practical source and another one is ideal source. Okay, so independent source is further classified into practical source or non-ideal source, and ideal is the source which we generally use it for our analysis. Okay, why we are considering ideal is it will be easy for the analysis. That's why we are always work with ideal sources. But in general, this ideal sources is not available. Only practical sources available. The difference between this practical source and ideal sources, this practical source will be having its own laws. Okay, the practical sources will be having its own laws within the source, whereas ideal source is considered as no loss source. Okay, so let me say about this again. We are broadly classifying the active elements as two things. One is voltage source and second one is current source. The voltage source is further classified into dependent voltage source and independent voltage source. Similarly, the current source is classified into dependent current source and independent current source. The independent current source is mentioned like this with a circle. For current source, we should mention this arrow mark symbol. Then for a voltage source, we should mention it with the plus minus, or you can use this battery kind of thing. Okay, so these are independent sources. Okay, independent sources. So these are the things. Then dependent source means you have to represent with the diamond symbol. Okay, you can see there is a diamond symbol. In the diamond symbol, if it is mentioned, it means that it is a dependent source. Okay, so dependent source. So in this dependent source also, we are having two things. One is dependent current source and second one is dependent voltage source. Why it is dependent, that we will discuss later. But dependent voltage source means you will be having plus minus. Okay, then dependent current source means within the diamond symbol you will be having arrow mark. Okay, so actually these things are not essential for your laboratory. So this you will be using in your subject only. This you will not be using in the laboratory. Okay, so we have seen what is this symbols of dependent and independent sources. We will see what is about individual things in the next slide. Okay, so this is about the independent voltage source. Okay, so we will draw it separately. I hope that my screen is visible to you. Okay, so consider that this is a source and there is a resistor. We'll take a simple circuit and we will analyze. Okay, we are going to mention, if you are having a source, within this you are having a source. This is your source. The source voltage we will consider something. Source voltage is Vs and this is your R. Okay, what will be the current flow through this? So this is your R, then your I will be V divided by R. This is very simple thing, you know it already, right? So here you are having Vs as the voltage magnitude. Now what we are doing, let us fix a voltage 10 for all the things. We will take four values. Only this resistor we will change, so we will mention it as a variable resistor. Okay, I have already told this is a fixed resistor. If you put an arrow mark like this, it is a variable resistor. Okay, so we will change the resistance value from, let take as 100 ohm first, then 10 ohm, then 1 ohm, then 0.1 ohm. Okay, so this is the actual terminal voltage. Let's say this is the terminal voltage, let's say that VT. Okay, so whatever the voltage across this will be the terminal voltage now for this condition. Okay, so now we will calculate the current. Okay, so the current for this first thing is 10 divided by 100, so you will get 0.1. Then here you will be getting 10 by 10, you will be having 1, and here you will be having 10 by 1, you will be having 10 ampere. Then here you will be having 10 by 0.1, so you will be having 100 ampere. So you can see here that the current flowing through this resistor is decided by the external elements connected to the source. Mean that what is the current through this voltage, or what is the current from the voltage source? Who is deciding the current from the voltage source? The current from the voltage source, we are fixing the voltage magnitude, but we are not fixing the current value. Okay, so if you give some voltage magnitude, we are fixing it the voltage magnitude. If you change the resistance value, it means that the current is going to flow, right? So if you give some resistance, some current will flow. If you change the resistance, accordingly the current will flow. So you can see here that the current is increasing. You can see that the current is increasing in this way, right? So initially it was 0.1 ampere, and later on for the final resistance of 0.1 ohm, you are getting 100 ampere through this path. Okay, so this is an ideal independent voltage source. An ideal independent voltage source can supply infinite amount of current. Okay, if you keep this resistance value, if you keep this resistance value as 0, then 10 divided by 0, you will get infinite ampere, right? So this ideal independent voltage source can give infinite amount of current. Okay, if you keep the resistance value as 0. Here the current coming out of the voltage source is decided by the external elements. What is the external element connected here? Here the external element connected here is the resistor. That external element is going to decide what is the current coming out of the voltage source. If the resistance is 100 ohm, then we will be getting the current of 0.1 ampere. Then if the resistance is 0 ohm, you will be getting the current as infinite. Okay, this is for an ideal independent voltage source. An ideal independent voltage source can supply infinite amount of current. That is the first thing. And the second thing is, this is the first thing, the ideal independent current source can supply infinite amount of current. That is the first thing. And the second thing is, within the voltage source there is no power loss, or there is no loss occurred within the source. Let's consider this is the complete source. Within this source there is no power loss, or there is no voltage reduction. So whatever the voltage across this, that is a 10 volt, that will be across the terminal, that is 10 volt. Okay, why I have taken it as a terminal voltage, that I will tell in the next part. But here this ideal independent voltage source can supply infinite amount of current with no loss. Okay, loss in the sense, generally it is a power loss. There is no power loss within the source. But if you consider a practical source, let's consider that actually battery is a practical source. So generally we will mention the practical battery like this. Okay, this represents that it is an ideal independent voltage source. Okay, this is also the symbol for battery. Okay, this battery generally will be having a resistor in series. I will tell why. So here in general the source will be considered like this. Okay, generally if you consider a battery, that battery will be having its own internal resistance. own internal resistance. Because of that, what will happen, own internal resistance it will be having. So because of that, what will happen, so earlier same case we will consider. Okay, so same case we'll consider, this internal resistance value will be very less. Let's consider that 0.1 ohm for easy calculation. Okay, again we will consider this as 10 ohm. Then now you put a same resistor, and here this is the variable resistor, and here also we will consider terminal voltage, that is VT. This is VT, and here the source voltage is 10, Vs is equal to 10. Okay, this Vs is equal to 10. Now we will see what is the voltage across this. In the earlier case we had considered infinite amount of current, no power loss, and Vs is equal to terminal voltage. Now we will see for this case, so same conditions we will consider. Vs is Vs I R L, this is R, then this is internal resistance, this is R internal. So this is R internal, this is 0.1 ohm. This R internal is not going to change. So this is 10, this is 10, this is RL, this is RL, or this is R internal. So this is 10, this is 10. Okay, we will start from 100 ohm. So if you find current, it will be 10 divided by 100 plus 0.1 ohm. So what is the current flowing through this circuit? You know that you are having a circuit like this. If you are having a circuit like this, then the current flowing through this path is, let's say that this is R1 and this is R2 and this is voltage V. So the current flowing through this path is I is equal to V divided by R1 plus R2, right? So this you know, right? So here the R internal is like this, so we will get some ampere. So now this current will be lesser than the previous current. There we got 0.1. Now we will get some current lesser than that, right? Because we have increased the resistance. Once we increased the resistance, the current will reduce. So now the current has become 0.0999. Okay, earlier it was 1 ampere. Okay, so now this is not a significant change. Now you reduce the resistance value, so we will consider 10 ohm. So internal resistance is 0.1, this is 0.1, then this is 1 and this is 0.1. Now you see the current here. So 10 divided by 10 plus 0.1. Okay, so now what will happen? If you see, now the current will become 0.99. Okay, earlier this was 0.1, this was 1. Okay, earlier for the ideal source. Okay, and for this case 10 divided by 0.1. So here we will get 9.09 ampere. So earlier it was 10 ampere. So for here we will get 0.1 plus 0.1, we will get 0.2. So earlier what we got, earlier for the same case we got 100 ampere, here we are getting 50 ampere. So earlier we got 100 ampere. So you can see here that because of the internal resistance, what is happening, there is a loss within the source. This internal resistance is within the battery itself. This is a resistance which is within the battery. You know that battery will be mentioned like this. You would have seen a battery, right, in your home. That wall clock battery and all, it is there, right? That battery will be having a finite resistance. For simple calculation I have taken 0.1, but it will be much lesser than this. Okay, so what it is doing is, when the current is increasing, means when the external resistance is reducing, you know that if the resistance is reduces, current will increase, because I is equal to V by R, right? So if current is increasing, then what happens is the power loss within the source is also increasing. Why it is increasing? So 10 is the voltage, their resistance is or internal is 0.1 ohm. So let us consider this case. Let us consider this case where the R load is also 0.1 ohm. Okay. So initially we are considering voltage as 10 and the current as 50 ampere here. So what is the power loss across this resistor? You know very well, power is nothing but I square R, right? So 50 square into 0.1. This is the loss which is occurring within the source. This is not an external resistance. This resistance is available within the source. That source is making a power loss within the source, right? So why it is making? It is having a finite resistance. Why it is having a finite resistance? It is a practical voltage source. In a practical voltage source, we will be having a finite resistance in series that will cause a power loss. Okay, so you will be having a question: why I draw a resistor in series? Why I did not draw a resistor in parallel? Actually, what is happening is, in a battery, what is happening is, what they understood is, when you are increasing or when you are drawing more current in the resistor load, if you are drawing more current in the resistor in the load, then what is happening is, the voltage across this terminal, this is voltage across the terminal, this is VT, this terminal voltage is going to reduce. That they have understood. Okay, so when the current is increasing, when you are having a practical source, if this is a practical source, what they understood is, if it is a practical source, what they understood is, when the current value is keep on increasing, then the power loss inside the source is increasing. That is one thing. And the second thing is, the terminal voltage is keep on reducing. Okay, the current is increasing, so the terminal voltage is keep on reducing. If the terminal voltage need to be reduced when the current is increased, then where the resistor should be connected is, the resistor should be connected in series. Okay, series parallel, maybe you are aware. I hope you are aware about the series parallel connection. Okay, series connection mean, if you are having a resistor, let's say this is a resistor. If one end of this resistor is connected to the another end of the another element, then these two elements are in series. Okay, suppose if you are having a two resistors, if you are connecting only one point with this, then these two elements are in series, and this can be connected with some other element. Okay, this can be connected with some other element. If these two resistors are, both the terminals of these two resistors are connected like this, then these two resistors are in series. Sorry, these two resistors are in parallel. Okay, when only one terminal is connected, then you can say that these two elements are in series. When both the terminals are connected like this, then you can consider it as a parallel. This is a mere simple explanation for us. This is sufficient now. Okay, so if a resistor is connected in series with the voltage source, if a resistor is connected, okay, resistor is connected in parallel with the voltage source, in parallel circuit, these two, actually here these two elements are in parallel. Now only I told that if you are having two elements, and if you are connecting both the elements like this, if you are connecting both the terminals of this elements like this, then this is a parallel connection. Okay, so here these both the elements are in parallel now. So whatever the voltage across this voltage source, that will be appearing across this parallel element. In short, you can say that if the elements are connected in parallel, if the elements are connected in parallel, then the voltage will be same across each element. Voltage will be same across each element. each element which are connected in parallel. Okay, so here two elements are there, so voltage across both the elements will be same. If you are having another element like this is also parallel, so the voltage across all the three elements will be same. Okay, so if you are connecting in parallel, the voltage will be same irrespective of the current flow in the external. Okay, so let's consider that this is an R internal. If you are adding an internal resistance, then some current will flow through this path. If some current is flowing through the path, then also you can represent the power loss. Okay, then also you can represent the power loss because it will be carrying some current within the source. Okay, if the R internal is connected in parallel, then also you can represent the power loss, but you cannot visualize the reduction in voltage, that is the terminal voltage, when there is an increase in current. Okay, the point is when the current is load current is increasing, your terminal voltage is reducing. If your terminal voltage need to be reduced, you should connect a resistor in series rather than in parallel, because if you connect the resistor in parallel, even though it may represent the power loss, it cannot represent the voltage drop, because if the current is increasing, if you are connecting the resistor like this, then it will provide infinite amount of current. There is no there is no voltage drop between the source and the load. Okay, so irrespective of the current you consume, it is going to give infinite, it is going to fix the voltage value as 10. But in practical scenario, they found that the voltage is also reducing. So this resistor is going to signify two things. One is there is a power loss within the source that we are representing with a resistor. Then why it is connected in series, we also need to mention the reduction in voltage when there is an increase in current. So for that we are considering a resistor in series. Okay, so let us proceed. So here you are having a voltage source, then you are having a resistor in series. This is the symbolic of practical voltage source. So here the practical voltage source cannot provide infinite amount of current. In the previous case, we considered that the independent voltage source can provide infinite amount of current. Here it is not possible. For practical source, due to its limitation, it is not possible to supply infinite amount of current. This infinite amount of current is possible only for ideal condition and only in theory. This infinite amount of current is not possible for practical condition. And the second thing is, here power loss is there. Power loss is there within the source itself, within the source itself. Okay, so here the terminal voltage, it can be either okay, terminal voltage can be either less than or equal to source voltage. It cannot be, terminal voltage cannot be greater than, no, okay, we'll consider this. We'll just consider that terminal voltage will be less than the source voltage at all the condition. You consider this. In the previous case, the terminal voltage was equal to source voltage. Here the terminal voltage will be less than the source voltage always. This is the basic difference between the independent practical voltage source and the independent voltage source. Okay, so this practical voltage source, in the ideal condition and practical condition we have seen. So for ideal condition, we had infinite current and no power loss, no loss, and Vt is equal to Vs. Terminal voltage will be equal to the source voltage. For practical condition, we had considered that it cannot be infinite and power loss is there, and terminal voltage is less than source voltage. Okay, so this is about these things. Then this is practical voltage source, both are independent only. Okay, now we will define what is independent. Okay, what is independent? Here, even though the terminal voltage changes, you can see that the voltage that we are representing for the source, this voltage is not at all changing. This never changes for an independent voltage source. This source voltage will never change for an independent voltage source. This voltage Vs does not depend on any other parameter on the circuit. Okay, so for example, so you are having a voltage source. This can be represented like this, or this can be also be represented like this. I have already told before. Okay, so here you can consider this, and here you can consider a resistor. Whatever the element you can connect after this. Okay, let's consider that this is terminal A and this is B. Irrespective of whatever the element connected after this points A and B, this source voltage will never change, means that the voltage magnitude does not depend on any other thing, does not depend on any other parameter on the circuit. Okay, since it is not depend on any other circuit parameters, you can call this as an independent voltage source. It is also suitable for practical voltage source. So two conditions only, one is ideal and another one is practical. For both the things, this Vs is not going to change. Okay, so both are independent voltage source. Okay, both are independent voltage source. This source voltage is not going to change at any case. Is that clear? If you have any doubt on this, you can ask, else we will proceed further. This is mainly about the independent voltage source and independent voltage source, where we have classified it as ideal and practical. Is that clear? If you have any doubt, you can ask, else we will proceed further. Shall I proceed further?
Yes, sir.
Yeah, fine. So similarly, we are having independent current sources also. Okay, so for that we'll directly go here. Okay, here I have plotted, this is ideal voltage source. This VAB is nothing but the terminal voltage. So irrespective of the current, your terminal voltage is not going to change. This is for the ideal condition. That's what I had mentioned here. Okay, then this is the circuit I had considered for the practical source. For that, this is the figure. This is the plot. So here, as the current increases, you can see that the current is increasing. The current is increasing. Because of the current, the voltage drop in this resistor is increasing. Okay, if the current is increasing, the voltage drop in this resistor is increasing. It is very obvious. Let us consider that this R internal is 1 ohm. If 5 ampere is flowing in this path, then 5 volt will drop across this resistor. If 50 amps is passing through this resistor, then 50 volt drop will be there across this resistor. Okay, so it means that when the current is increasing, the voltage within the internal source will be increasing. That is one thing. So if the voltage drop within the source is increasing, then the voltage across the load will be decreasing. Okay, that's what it signifies. VAB is reducing when the current is increasing, whereas the internal voltage drop is keep on increasing when the current is increasing. That's what they have mentioned here. Here I have detailedly explained about how much power loss is there when there is an individual current. Okay, that I have mentioned it here. Okay, this is just for understanding. Okay, so this will be taught in your theory. Okay, so that's why I'm not uh, focusing much on this. Okay, so sir will teach you in the class. Whether sir has started taking classes for you? Hello. Whether the subject, whether the classes are started for this subject? Can anyone respond?
No,
Sir,
sir,
what
not
would be
yet.
the topic of that class?
Principles of electrical engineering and measurement.
No, sir, that is not started.
Last week you did not had any class. Today
Sir, only two
you are
class we
supposed to
had
have
last
class.
week.
Okay, today first hour you should be having, first hour or second hour you should be having principles of electrical engineering and measurement, right? Today morning 9 to 10 or 10 to 11 you are supposed to have principles of electrical engineering measurement, as far as I remember. Is it right? Okay, fine, leave it. That is out of our scope.
Sir, it is 5 to 6, I think, today.
Okay, okay, fine. Okay, so now let us proceed. So similar to voltage source, we are having independent current source. So in independent current source, similar to the previous case, this current source can provide same amount of current magnitude if the current magnitude is 10 ampere, irrespective of the external element connected. Irrespective of the external element connected, after this, the current coming out of this terminal is 10 ampere. Okay, if the current source magnitude is 10 ampere, the current coming out of this terminal A is going to be 10 ampere. Okay, so here Is will be equal to the current coming out of this terminal Ia. Okay, let us consider that the current coming out of this terminal is Ia, or you consider that the current coming out of this terminal is IR. Okay, so the current coming out of this terminal will always be equal to the source current. Okay, this is for the ideal current source. For a practical current source, what we are going to have here, we are going to have the resistor in parallel instead of a resistor in series, like how we had considered in the previous class. Here the internal resistance is connected in parallel rather in series when compared to the previous case. Why it is considered in parallel here is, as you know, see, actually what they understood is when the voltage across this resistor is increasing, when the voltage across this, consider that across this terminal, when the voltage across this terminal is increasing, then what happens is, then current through this path is, okay, will not mention like this. Let's consider that the voltage across these terminals are increasing, then there is a power loss within the current source that they have found. Okay, so you are having a current source, then you are having a resistor. Okay, so instead of changing the, you are changing the resistor value, you are changing the resistor value in such a way that the voltage across this element is going to increase, or you can say that the voltage across this terminal is going to increase. Okay, so this is the case. First they have considered Is is equal to 10 and R is equal to 0.1 ohm. For that the voltage is I into R, that is 1 volt. Okay, the voltage across this resistor is nothing but I V is equal to I into R. Already I is given, that is this I, this is given, this is going to flow through this path. Okay, now when the voltage is current is same for all the elements, and the resistance we are changing. If we are increasing the resistance like this fashion, the voltage across this resistance is going to increase. Okay, what people found is, when the voltage across this terminal, this is A and B, when the voltage across this terminal is increasing, the voltage across the terminal will be equal to the voltage across this resistor. Okay, so when the voltage across this terminals are increasing, then what they found is, there is a power loss within the source and there is a current reduction within the source. There is a power loss within the source and there is a current reduction within the source, means that the current coming out of the terminal A is going to reduce. Okay, that they have found. So if they want to incorporate these two things, they can incorporate this. There is a resistor like how we had considered before, and they can connect a resistor like this and they can mention like this. So if you connect the current source like this, it means that this resistance, that is our internal resistance, that is going to represent the power loss. That is going to represent the power loss. However, these elements are connected in series. If these elements are connected in series, the current will not change. Okay, like we considered in the previous case, when you are having a voltage source and a resistor in parallel, the voltage across these two elements will be same, right? Similarly, when you are connecting two or more elements in series, you are connecting two elements in series. Let's say that I'm saying that I'm adding one more element. So these three elements are in series. So if I say that 10 ampere is going to flow through this path, then the 10 ampere will come through this path. Okay, there will not be any reduction in current. So if there is a reduction in current, they cannot represent the practical current source. In order to represent the practical current source, they have to show the current reduction. Also, they should represent the power loss. In order to represent that both the power loss and the current reduction within the source, they have used a resistor in parallel. Okay, so if you are connecting an element in parallel, there will be a current division. So because of that, the current will be flowing through this path. Okay, so that's why for a practical current source, you will be having a current source connected in resistance with the connected a resistor in parallel with respect to the current source, so that it indicates the power loss and current reduction. So what it means is, if the voltage is increasing across the terminal, the entire current magnitude of the source is not coming to the terminal. Okay, that's why it is mentioning. Okay, one more thing you have to notify here is why it is called as independent current source. Like I said before, irrespective of the external circuit element, any element, whatever the element you connect after this current source, the current coming out of this current source is not going to change. The current magnitude of this current source is going to be a constant or steady value, irrespective of the element you are connecting here. Okay, except the R is equal to infinite. Okay, means if you are connecting a current source like this, and if you are having a resistor here, then this is I, and if you keep this R as infinite, so except this condition, this is not the condition we should consider. Except this condition, whatever the resistance value, the current coming out of this source will never change. Why I am saying this condition? When R is equal to infinite, it means that no current can flow, so you should not consider this thing. So when R is equal to infinite means, it means that there is no resistor available here. R is equal to infinite indirectly says that there is no resistor. This is called as an open circuit. This is called as an open circuit where there cannot be a current flow. Okay, if R is equal to 0, it means that this is R is equal to 0 symbol. So this is called as short circuit. Okay, so these things you would have studied, whatever I have told you till now, you could have studied in your 12th standard or your competitive examination. So here, if it is mentioned like this, here the R is 0, also the voltage is 0. If it is mentioned like this, then it means that the R is infinite and the current is 0. Okay, so this is for open circuit. For short circuit, voltage is 0 and the R is 0. Is this clear?
Yes, sir.
Okay, so one thing you note it down. One thing you be careful. See, if you are having a voltage source like this, and if you are having a resistor, if okay, let me complete this. Then if you are having a current source and if you are having a resistor, why do I want to tell you this? Okay, so here for a voltage source, let's say that the voltage magnitude is 10, the resistance value is changing. So the current coming out of this source is dependent on this resistor. Okay, similarly, the voltage across this terminal is decided by the current source. So what I want to say here is, one thing you make sure, the current through the current from the voltage source is dependent on the external element. Similarly, the voltage across the current source. Similarly, the voltage across the current source is depending on the external element connected. If you connect, let's say that the current is 10 ampere and the resistance is 1 ohm, then the voltage across this current source is 10 into 1. It is a parallel component. You can see that both the components are connected in parallel. So whatever the voltage across this resistor, that will be appearing across this. Okay. One thing I wanted to make you clear here is the voltage across the current source is never zero. Means always people consider that if there is a voltage source, there is some current flow from that voltage source, that people will agree. But generally what do they forget is the voltage across this current source. Generally what do they consider? It is a current source, it is going to supply 10 ampere. Then if you ask about the voltage, they will consider that the voltage across the current source as zero. Okay, this is not true. The voltage across the current source is not zero. The voltage across the current source is dependent, is decided by the external element. Similarly, the current coming out of the voltage source is decided by the external element. Okay, is that clear? The voltage across the current source is not zero. It is depending on the external element connected to that circuit. Is that clear?
Yes, sir.
Yes, sir.
Yeah, so that you make it clarified. So other than that, when the voltage is increasing, the current coming out of this terminal is reducing. That's what it signifies. Similarly, when the voltage is increasing, the internal current is increasing. So the current through this internal resistor is keep on increasing when the voltage across the element is voltage across these terminals are increasing. Okay, that's what I have mentioned in this slide. Okay, so let us talk about the dependent voltage source. In dependent voltage source, there are two things. One is voltage controlled dependent voltage source, and second one is current controlled dependent voltage source. Okay, as I had already said before, the diamond symbol represents that it is a voltage, it is a dependent source. If it is a plus minus, it represents the voltage source. This diamond symbol represents the dependent source, and this plus minus represents the voltage source. This is going to represent the dependent source, and this plus minus going to represent the voltage source. Okay, then why they are saying voltage controlled voltage source and why they are saying current controlled voltage source? Okay, you can see this parameter alpha into V1, beta into I1. Okay, so in the earlier case, when we talked about independent voltage source, in the earlier case, when we talked about the independent voltage source, what we said, just a minute. Yeah. So this is an independent voltage source. What we said, this, let's consider that this is Vs. We said that the voltage Vs is never dependent on any external element. That's why we said it is an independent voltage source. Now, this dependent voltage source, that's voltage magnitude of this dependent voltage source is going to be decided by some other element. How I will say. Okay, let us consider a simple circuit. See, in this circuit, we are going to have a current flow here and we are going to have a current flow here. Okay, this R1 will be having some value. Let's say R1 is 1 and R2 is 2. Okay, so if you have some resistance value like this, let's consider this alpha is a constant for time being with this alpha as 1. Okay, this is alpha as 1. So now you can see it is mentioned as alpha into V1. It was mentioned as alpha into V1. So what is V1? That V1 is the voltage across the resistor R2. Okay, the V1 is the voltage across the resistor R2. Okay, so if we are applying 10 volt source here, then because of that some current will flow, because it is a circuit, because complete paths are closed. So because of that some current will flow through the R1 and some current will flow through R2, right? So let's say that the current through this R2 is I1. So what will be V1? V1 is the voltage across the resistor R2, that is given by I1 into R2, because I have mentioned that I1 is the current which is flowing through this resistor R2. So this voltage magnitude is V1. So if this voltage magnitude is V1, That is the voltage magnitude for this dependent voltage source. So for time being, we had considered this alpha is equal to 1. The voltage magnitude of this dependent voltage source is 1 into V1. If the V1 is 10, here the voltage magnitude of this source will be 10 volt. If the V1 is 20, the voltage magnitude of this source will be 20. And if the voltage V1 is 30, then you will be getting the voltage magnitude as 30 for the dependent voltage source. So what I want to say here is this voltage source magnitude, this voltage source magnitude is given by alpha into V1. That V1, this alpha is a constant, so you forget about it. So this V1 is completely dependent on some other parameter. Some other parameter means here this voltage is dependent on the resistor here, right? So that's why this voltage magnitude is dependent on some other circuit element. So this is a dependent voltage source. Dependent voltage source in the sense this voltage magnitude is decided by some other parameters voltage. Okay, so it is a dependent voltage source. Then why it is called as a voltage controlled voltage source? See here, the parameter which we are considering is V1. V1 is nothing but the voltage measured across the resistor. If V1 is the voltage measured across the resistor, and if that is deciding the voltage of this source, then it is a voltage controlled voltage source. That's why I said when the V1 is increasing, then the voltage magnitude of the source will also vary. Okay, that's why this is called as voltage controlled voltage source. Okay, and the second one is current controlled voltage source. So instead of the V1, if you consider that the current flowing through this resistor R2 is deciding the voltage magnitude of this source, then you can consider that as a current controlled voltage source. If the voltage value is deciding the magnitude, then you can consider it as voltage controlled. If the current magnitude is deciding the magnitude of the source, then you can consider it as current source. Okay, current controlled. Okay, not current source, current controlled one. So here, this resistor R1, it's going to see a current of I1 flowing through this path. So that I1 is going to decide the voltage magnitude of this dependent voltage source. So let's consider for time being beta is equal to 1, and if I1 is 10 ampere, then voltage magnitude is 10 volt, and if I1 is 20 ampere, then voltage magnitude of the source is 20 volt. So the current is deciding the voltage source magnitude, so it is called as current controlled voltage source. Here it was considering the voltage magnitude is decided by the voltage across some other element, so this is a voltage controlled. Okay, is that clear? This is the very basic thing. Actually these are not required for the lab. Since I have started, I just want to complete that. Okay, is that clear?
Yes, sir.
Okay, so similarly for dependent current source. Okay, so dependent current source in the sense the current source, as I said before, for a dependent source we should mention with the diamond symbol. If it is a current source, we should mention with the arrow mark. Arrow mark represents the
Current
arrow mark
source.
represents, sorry,
Current source.
yeah, arrow mark represents the current source. Also the current is coming out of this terminal. Okay, so now this current source can be a voltage controlled current source, or it can be a current controlled current source. Voltage controlled current source in the sense, here if the voltage of this resistor R1 is controlling the voltage current magnitude of this source, here like the previous case we are having one constant multiplied by this V. So here this voltage across this resistor, that is V, it's going to control the current of this current source, so it is a voltage controlled current source. Similarly here the current magnitude of this current source is decided by the current flowing through this resistor R1, so this is a current controlled current source. Okay, I hope that this is clear for you. So if this is clear, we can proceed further. Only one thing is, here in the dependent source, the voltage and current magnitude is decided by some other circuit element, whereas in the independent current source or voltage source, the voltage or current magnitude was not decided by some other parameters. Okay. So let us proceed further. So this is Ohm's law, you know very well. V is equal to IR. For a constant temperature, V is equal to I into R. So if you vary this resistance, if you vary this resistance is a proportionality constant. If you are increasing the I, it will be increasing the R. Sorry, it will be increasing the V. In another way, if you keep this R as constant, if you are increasing V, I will be increasing. Similarly, if you are increasing I, V will be increasing. Okay. So these things sir will teach you in the class. I think that is not required. So only one thing again I want to say here is, when R is equal to infinite, it is an open circuit. I told before, this is a resistance. For this resistance, if this resistance value is infinite, then this is an open circuit. Then if the resistance value is 0, then it is a short circuit. So here the current is equal to 0. Here the voltage across the terminals, is equal to 0. Okay, so why I am saying this, these things you require. Okay. Just a minute. So we talked about R internal, right? We talked about R internal for the practical voltage source. So what is the R internal for the ideal source that we have to consider for voltage source and current source? For practical voltage source, we had R internal, that R internal is connected in series. For a practical voltage source, what is R internal? For practical voltage source, we are having R internal. What is the R internal value for ideal voltage source? That's what we have to see now. Okay. So you know that I is equal to, what do we need? We need R. R is equal to V by I, right? So here you are going to measure the current, right? Here, let's say that you are going to measure this current. Just a minute. Okay. So as of now, you just consider that the R internal resistance is 0. R internal is 0 for practical voltage source. Then for practical current source, the R internal is infinite. Okay. Why? Because for a practical, for an ideal current source, there is no voltage drop within this source. So if there is no voltage drop and there is no power loss within the source, obviously the resistance of the series path should be 0. Okay. Because of the reason, the R internal should be 0. Okay, there is a plot for this, so that you can easily understand that suddenly I am not getting it. So other than this, for for ideal current source, we are having the current source like this, and we don't have any current division within the circuit. That means that there is an open circuit. So for this, the R internal is equal to infinite. So if this is the case, you are going to have this R is equal to infinite. If you have R is equal to infinite, as I told before, the current flowing through this path is 0. So the internal resistance for this circuit is, for this ideal current source is infinite, and infinite and the R internal for the ideal voltage source is 0. Okay, just a minute, let me check. Just a minute, give me some time. Am I audible?
Yes, sir.
Yeah. So let us find the slope for this plot. So R internal can be find it out. R internal can be find it out using the slope. So here you just find the slope. So let us consider this is V2, V1, this is V2, and this is I1, this is I2. Okay, so you just find slope here. You find del V divided by del I. So if you find del V divided by del I, so you can see here that the voltage remains constant. So you will be having the voltage as 0. Then the current will be having some value. Okay, irrespective of that, you are having del I. Irrespective of that, you are going to have a 0 value. That is what your R internal. Okay, this is going to give the R internal for this source. Okay, so here what we are doing, here we are plotting the current coming out of this source. Okay, this source is going to give infinite amount of current irrespective of the voltage. So here the source voltage you are plotting source voltage with respect to the current. You know that even if it goes to infinite amount of current, this voltage magnitude is going to remain constant. So if you plot that, if you take the slope of that, you can say that 0 divided by del I, so that is equal to 0. This is nothing but our internal resistance. Similarly, for the current, if you plot, so this will be the current, this will be the, so if you take I and V like this, so there I will be constant and voltage will be varying, right? So if you take the slope for this plot, then you will be getting R is equal to infinite, or you can also draw it in the reverse way. In the same plot, you can take, like, you can consider like this: voltage is changing and current is like this. So for this, you are plotting the current source, so you are getting the irrespective of the voltage, your current is going to be same. So if you take slope for this, again the slope will be here actually del I divided by del V. But what is your motive? Your motive is to find resistance. Resistance is nothing but del I divided by del V. You will be getting I del I as 0, del I as 0, and you will be getting del V here. So this is actually 1 by R. This is actually 1 by R. So if you take the reciprocal of this, you will be getting del V divided by 0. So then you will be getting R internal as infinite. So that is the reason why the internal resistance of this voltage source is 0, and why the internal resistance of the current source is infinite. Okay, so I think this is sufficient for us to proceed for our lab thing. So hereafter we will not see much about this topics, and the basic relation is V is equal to I into R as per Ohm's law for a constant temperature. Okay, so we will proceed with two more things. Terminal, if you are having a resistor, if you are having any element, if you are having any element, and this is one end and this is second end. Let's say that this is end one, this is end two. So these two ends are called as terminals. Okay, this element is called as two terminal elements. So any two terminal element can be called as a branch, irrespective of whatever the element you connect here, you can call it as a branch. Okay, so your resistor can be called as a branch and inductor can be called as a branch here. Similarly, the capacitor can be called as a branch. Voltage source, current source, whatever the two terminal elements you do have, you can call it as a branch. Then node. Node means, let us consider that you are having a resistor and you are connecting with some other element. You are having, okay, let's say that you are having a terminal. So that terminal, let's say that this is terminal 2 and this is terminal 1. Okay, and if you're adding another element, it can be a resistor, whatever it may be. So this point which is connecting these two elements is called as a node. Any point which is connecting two elements can be called as a node. Minimum two elements. Okay, if any point which is connecting two or more elements, you can call it as a node. Okay, so if it is connecting minimum of three things like this, let's say that you are having three things like that here, minimum three or more elements are connected, then you can call this point as junction. If two or more elements are connected at a point, you can call it as a node. If three or more elements are connected, you can call it as a junction. Okay, so that's what I have mentioned here. So here we have considered three elements. Here you can call either this as a node or a junction, and but this is only a node, not a junction. Okay, so this is one thing. This junction I have mentioned here. Then loop means closed path. Okay, loop means closed path where the current can flow. Okay, closed path where the current can flow. So here in the circuit, A, B, C, D, A is a closed path. So this, in this path current can flow. So this is a closed path. Whereas this B and C, let's say that this is E and F. Okay, E and F. You can consider this B, E, F, C, B as open path, or there is no path actually. So it is a open circuit you can call. Okay, in this open circuit, you can consider that the resistance, there is a resistor here and that resistance value is infinite. You can also consider like that. Okay, but this R is equal to infinite. So if the R is equal to infinite, then you will consider it as an open circuit. There is no current flow through that path. Okay, so then series and parallel. Actually, I hope that you would be aware of series and parallel combination. In series path, two or more elements are connected, then same current will be flowing through the series path. Whereas in the parallel combination, the same voltage will be appearing across the parallel combination. For this circuit, let's say that for this circuit, let's say okay. So for this circuit, R1, R2, R3 are in series, because whatever the current coming out of this, that will be flowing through all the resistors. So it is a series path. Okay. If you see here, the same voltage, whatever the voltage across this voltage source, that will be appearing across this resistor R1. Similarly, the same voltage will be appearing across this R2. So this is a parallel circuit. Okay, in parallel circuit, voltage will be same. In a series circuit, the current will be same. Okay, so in this circuit, if you consider R3, R4, R5, these three elements are in series. The effective resistance of this value is in parallel with this R2. Okay, so that we will see, that we will not see, you will see it in the class, that I'm not going to tell you, you may be knowing also, so that we are not going to see it. Okay, then uh, then we will see. Okay, then directly we will go to the Kirchhoff's laws. So if you have any doubt till now, you can ask, else we can proceed. These are the very basics. Still you may be requiring more basics, but I'm not taking into that because it will take long time to complete it. It will be again, it will be like I'm taking class. Okay, so that's why I'm not taking. If you are interested, you can take the recorded video from ECB section. I have taken class for it. Shall I proceed?
Yes, sir.
Okay, so this, of course, you would know, you would have studied Kirchhoff's current law and voltage law. So we have talked about a node. Node means connection of two elements. So let's consider that we are having two or three resistors like this. So you can just forget about what is the element connected here. So instead of mentioning it in the elements point of view, I'm just mentioning it in the generalized point of view, irrespective of any element connected here. Irrespective of any element connected here, this law holds good. That's why I have suppressed that element. Okay, so Kirchhoff's current law says that the sum of charges at this node will always be equal to 0. If you are having a node or junction, the sum of charges with at this node will be equal to 0. That's what our law of conservation of charges says. So if you sum the charges algebraically at this node, it will be equal to 0. If you extend that with respect to current, you can say that the sum of current at this node will always be equal to 0. So in another way, if some current is entering and some current is leaving, then okay, we'll mention some current entering so that it will be easy to understand. So you can say that the sum of currents entering at this node and the leaving at this node will be equal to 0, or in a generalized way you can say that the sum of currents at this node will be equal to 0. The summation of current at this node will be equal to 0. That is one thing you can say. Or summation of incoming currents equal to summation of outgoing currents. So this way also you can mention. So here for incoming, it is a general procedure. So you can consider that incoming current is equal to outgoing current. So like this you can consider. Okay, so if you have a circuit, if you are having a node like this, then if I say that 1 ampere is coming here and this 2 ampere is coming here and some current is coming out of this, this is X. So two currents are coming in. Coming in means at this node, if you are seeing two currents are coming towards you. So if two currents are coming towards you, then you can say that currents are coming in, right? So if that is the case, I said sum of the current incoming, that is 1 plus 2, will be equal to the sum of currents at the outgoing. In the outgoing, you are going to have only one current here, so your X will be 3. Okay, so like this you can write, or in other way, sum of the currents is equal to 0. That also you can write. If you are considering sum of the currents is equal to 0, so for that condition, you consider that incoming current as negative. Okay, minus I1, minus I2, sorry, minus 1, minus 2 plus X. Outgoing current as positive. So this is equal to 0. So now if you rearrange this equation, X is equal to 3. See, it is looking like mere a rearrange of equation, but whenever you are considering the incoming and outgoing at the same side, you have to mention it as sum of the currents. If you are mentioning it as sum of the currents, you consider incoming as negative and outgoing as positive. Okay, then only you will consider, you will get the right answer. Okay, but if you want to consider it in the reverse way, means if you want to consider the incoming current as positive and outgoing current as negative, that is also fine, there is no problem. But you follow one thing properly, you either consider incoming as negative or outgoing as negative, but you consider one thing properly throughout the solution. Okay, then only you will get the correct thing. That's why I have mentioned this is a conventional one. Current entering the node is equal to negative, and current leaving a node is considered as positive sign. This is a conventional. You can also consider in the reverse way, there is no problem with that. But if you are considering one thing, you consider it throughout the thing, you don't change it in between, else you will not get the right answer. So here what they have said, they have said the current sum of currents in a node or at a node will be equal to 0, or the sum of currents entering will be equal to the sum of current leaving will be same always. Is it fine? Of course you would have studied this. I know that you would have studied this in your 12th standard itself. So this is a circuit, this is part of a circuit. In this part of the circuit, if you consider any node, irrespective of any node you consider, this is the node and this is a node, this is a node, irrespective of any node you consider, you will get the KCL satisfied. Okay, other than that, this is a closed boundary summation that it's not required for you. Okay, that is not required for you. But if you considering any closed boundary, for that also the sum of currents will be equal to the sum of the currents entering will be equal to the sum of currents leaving, but this is not required for you. Okay, but mainly you can apply KCL at any nodes. Is it fine?
Yes, sir.
So in case if we will consider this circuit, in this circuit we are having three current sources. So these three current sources are connected in parallel. Okay, if these elements are connected in parallel, then see here, let's say this is terminal A and this is terminal B, this is terminal C, let's say. Okay, so these are in parallel. If there is a resistor connected in between this terminal, okay, we'll consider this is D, E, F. Okay, so if you have a circuit like this, now you can say that AD is parallel to B. Similarly, B is parallel to CF. B is parallel to CF. Also, AD is parallel to CF. You can say like this. Okay, for this circuit, in case if there is a resistor is connected between these two elements, if there is a resistor between these two elements, then you should not call AD as parallel to BE. This is not correct. AD, this current source, is not parallel to BE if there is a resistor in between it. Okay, so in detail, sir will teach you in class, that I am not going in depth, but you just understand that these two elements are not parallel if you are having a resistor in series like this. But again, this BE is parallel to CF. Okay, now the B is parallel to CF because there is no element connected here. Between these two terminal, there is no element connected. So you can consider that as a parallel elements. Okay, so we'll move back. So let's consider that there is no resistor and you are having the actual circuit like this. Then these current sources are in parallel. If these current sources are in parallel, then you can consider the summation of the currents, means this is in upward direction, and this is in also in upward direction, and this is in downward direction. Okay, you can represent that as a equivalent current source. You can represent a equivalent current source like this. So if you are representing in this direction the equivalent current source like this, then I3 plus I2 minus I1, because this I1 current direction in the downward side, whereas the other two currents is in the upward side. In case if you are representing this current direction in the downward side, then you can write I1 minus I3 minus I2. Okay, I hope that this is clear to you. So what I had considered is, I had considered the current direction. So based on that current direction, I had considered this I1's current direction as positive. So if I want to represent the overall current direction in the downward side, then it means that I1 is greater in magnitude when compared to the summation of I3 and I2. Okay, if I want to represent as a equivalent current source, and I am representing that in this downward direction, it means that I1 is having a greater magnitude than I3 and I2. Summation of this will be greater than this. Okay, that is one thing. If in case if I3 and I2 are greater, then obviously I will get a negative value here. Negative cumulative value I will be getting. Negative current I will be getting. Okay. So this is as of now it is not required for you. If current sources are in parallel, you can have a equivalent current source. Depending on the current direction you given, you can find it out whether you have to add it or subtract it. That is one thing. Okay. Here again I repeat, the current sources are in parallel, but you cannot connect any two current sources in series. Actually, you are not supposed to connect. I will say later why. If you are connecting two current sources like this, let's say this is 5 ampere and this is 6 ampere. Okay, in this case, actually this will violate KCL. This will violate KCL at this node. Okay, after this you forget what is the circuit. After this you forget. This will violate the KCL at this node because the current entering this node is 6 ampere, whereas the current leaving this node is 5 ampere. This is not at all possible. Whatever the circuit you have, whatever the network you have, that should be following KCL and KVL. Without following KCL and KVL, no circuit can be there. Okay, so in order to make this circuit working proper, what it will happen, the current flowing through this circuit will be 5 ampere only. Means what is the least resistance it is having, that current only will be flowing through this path. So why I am choosing like that, if I consider like that, you can see here that the KCL will be KCL will not be violated. Okay, so that's why if 5 ampere is flowing through this path, then in this node, so I am having a circuit here. Okay, you are having a resistor here. Okay, if you are having a 6, initially we are having 6 ampere here and 5 ampere here. So if you apply KCL at this node, it will not follow the KCL, it will violate because incoming current is 6 ampere, whereas outgoing current is 5 ampere. Your KCL is violated. So this is not possible. So for this case, what will happen? The least current source magnitude will be flowing through that path. If least current is flowing through that path, then you can say that the KCL will not violate, so that the 5 ampere will be equal to the 5 ampere, that is incoming current is equal to the outgoing current. Okay, so this is the general representation of this thing. So always your KCL and KVL should not be violated at any case, irrespective of any circuit you have. It should follow KCL and KVL. Okay, so like how we have considered for KCL, similarly we can consider it for the voltage. Okay, leave it. Just a minute, it got stuck. Okay, will you come to the lab next week? Will you come to the lab physically next week?
Yes, sir. Probably we will be there.
Don't you have any, what do you call,
Sir, we have
this,
to arrive there by 15 November. So by next
okay,
week, I think that everyone will come.
don't you have this quarantine period? I don't know about that. That's why I'm asking. Don't you have any quarantine period?
Yes, sir. They have said that there will be a quarantine period, I guess,
So you will not
for
come to
Tamil
the,
Nadu and Kerala students. Mm.
for other people, you will come to the lab directly. Is it like that?
Sir, we don't have all information. The quarantine was allotted for those students who are from Kerala or Tamil Nadu, from those
Okay,
states.
so their students should have come now, then only they can go for the quarantine period, right?
Yes.
Okay, fine. Okay, fine. Let me complete KVL alone, then we can end this class. I think I already have taken long time. Okay, if you have any doubt, you can ask. Else, we'll see in the next class. I think it's sufficient for today. You can stop recording. My system got hang. You can stop recording.